Thanks to everybody for joining. My name is Randy. I am a manager at DreamWorks Animation in our production software tools department, and I'm excited to be talking to you guys all about the MoonRay production renderer today. One quick note, we have a lot of images from our movies in my deck, and every image that you will see is rendered by MoonRay. Another thing to note is that my session got moved from the afternoon. I got a little bit of shorter time. So I tried to trim down my slides, but I got a lot of material to go through. I'm going to read, but this is my own words, even when I read. Hello? It's my own words when I read, so I'm going to put on my reading glasses and walk you through this. So let's get started. We're going to review really an introduction to ray tracing, because MoonRay is a ray tracer. So I'm going to give you a brief, succinct introduction to ray tracing. Then I'm going to talk about MoonRay in particular, the production renderer we use for all of our feature films at DreamWorks. MoonRay was built on modern computing architecture with the intent to provide interactive scene visualization with the ability to selectively scale compute resources to suit each artist's workflow. And then we'll look at how MoonRay's development took place, and finally we'll discuss our motivation to open source this technology, along with our journey to get it out the door and the lessons we learned along the way. So an MCRT renderer, or Monte Carlo ray tracer, tries to emulate real-world light transport as accurately as possible, at least when we want it to. Sometimes we bend the rules to depict very unique and inventive worlds. So I'm going to start with this basic description of ray tracing, specifically the naive approach of forward ray tracing, or basically how particle transport works in the real world and how we humans are able to see things. So here we have a simple scene with a light source, some sort of polygon object, and a sphere floating in space, and this green happy face that is looking at the scene. Now, first off, our light source emits photons, and since we don't know if a photon is a particle or a field or a wave or all three of these things, we're going to pretend it's none of them. And we're simply going to approximate it by pretending it's rays of energy. And we're going to visualize what those rays are doing. Okay. So here we see a light source emitting rays in all directions in the scene. And we'll follow, as an example, just one of those rays that reaches a surface. Now, that surface isn't smooth, so it will reflect light into the environment in multiple directions. And one of those directions is towards the eye of our viewer, so they can see the polygon directly. But light will also be bounced towards other objects in the environment, and once it reaches that other object, it will also scatter light particles based on its surface properties. And one of those directions is towards the eye, but perhaps our sphere is transparent, and it will refract light through this object. Some will scatter out the back, but some will also be reflected back again through the object, and potentially also reach the eye. Now, this is very, very simplified, but it should give you a basic idea. Now, if we want to simulate this on the computer, we need to start tracing many billions of rays from this light source. However, only a vanishingly small percentage of those rays are ever going to reach our viewer's eye, so we'd be wasting an awful lot of computation. So in computer graphics, we simulate this with backward ray tracing, and we turn the problem around. In backward ray tracing, or what we simply call ray tracing, we'll put a grid of pixels in front of the eye and trace rays into the scene to see if they eventually hit any light source. In this way, we immediately eliminate all the light rays that never reach the eye, so we've already optimized our task. Then for each pixel, we trace a number of rays. Now, if we traced only one ray per pixel, you would see a very blocky version of this scene. But as you trace more rays per pixel, you get a better approximation of the final correct result, and thus it looks smoother. That's a side note. For now, let's concentrate on just one ray at a time, since the process is the same for each one. Let's start with this pixel and we see that the ray intersects the sphere. And it sends out some refraction rays. And at the sphere surface, we use importance sampling to pick good directions to sample in the scene. And we shoot rays out in those directions. We achieve this because we know which directions a light emits the most energy and which directions a surface reflects the most energy. And instead of shooting rays out in all directions equally and wasting compute, we can choose from those directions and combine the probabilities using what we call multiple importance sampling. Yes, one ray from the eye fractures into multiple rays as it encounters each surface. And some of its surface sample rays will hit other objects, and other rays from the scene will also hit those objects, but at different angles and thus different sample patterns. And we keep this up until eventually something finds a light shining on it, and we return the color of the pixel. We repeat this over billions of rays, and an image comes out the end. So where does a path tracing renderer like MoonRay actually fit into the film production pipeline at DreamWorks? Here you can see the various departments involved in the process, and while not strictly always linear, there is a certain flow between upstream departments handing down to downstream departments. Now, there is clearly one spot that absolutely needs to be there, which is rendering or capturing all the final frames in our movie. Let's see if this works. That's somewhere over there. However, rendering happens in many departments during the course of the show as artists iterate and refine their work over the course of the production. So a renderer in a feature production pipeline is very important. So let's continue on. MoonRay is our high-end production rendering system. It replaced Moonlight, our deep frame buffer micro-polygon rasterization system. Now, we were by no means the first major studio to make the change from micro-polygon rendering to path tracing, but we learned a lot from those who went before, and we approached the problem with a ground-up rewrite. As I mentioned previously, it is a Monte Carlo path tracer. It's 100% ray traced. It's easy to use and provides artists with fast iterations. It can be integrated into a wide variety of digital content tools, also known as DCC tools for short, such as Houdini, Maya, Katana, Blender, in-house lighting tools, etc., either with an appropriate plugin or with a USD Hydra render delegate, and I'll explain that last part in a little bit later. MoonRay's basic algorithm is best described as a backward path tracer with next event estimation and multiple importance sampling. We do provide MoonRay as a service to our internal clients, which are our shows, via our in-house cloud framework, which is called Eris. Not only does this simplify the application integration, but it also allows MoonRay to take advantage of massive machine-scale distributed rendering. MoonRay can render images that are photoreal. This is a render. The glass on the left is rendered. The one on the right is real. Or MoonRay can render the more fantastical, such as glittery dancing trolls. Let's move on. So shaders are basically plugins that describe lights, materials, geometry, and more. Moonshine is a package of capable production shaders that are included with our open source MoonRay repository. Here we have a wireframe mesh of our version of the standard shader ball 3D model. We've open sourced this model on the Open MoonRay website. And we can shade it into a plastic diffuse material in multiple colors. We can make it glossy, or like car paint, or iridescent, aged bronze, translucent. We can layer materials on top of each other, make it look like water, or as something frightening for Halloween. And these are all our shaders. Not all of our shaders, but this is an example of our shaders. So let's talk about MoonRay's architecture. We wrote it from scratch, leveraging state-of-the-art open source components where appropriate. No studio legacy code was used. It was a complete ground-up write. The architecture is cleanly divided across 3 different APIs. We have a rendering API for clients to initiate rendering, the shading API for the development of pluggable shaders or materials, and a procedural API for the development of geometry generators. We do use best-in-class open source libraries as part of MoonRay. So Embry is our ray intersection engine. It was initially developed by Intel for MoonRay, and then it was open sourced by Intel. We also use OpenImageIO to generically handle different image file formats. It was written by a developer from Pixar, and then NVIDIA, and then Sony when he finally got tired of writing the same library at every company he worked for, and he open sourced it. OpenSubdiv is an open source geometry library contributed by Pixar with major improvements from DreamWorks. OpenColor.io is a color management library contributed by Sony with an emphasis on visual effects and computer animation. OpenEXR is a professional grade image storage format in wide use in the motion picture industry, and it was developed and contributed by ILM. OpenUSD was mentioned in this morning's keynote. It's an open source scene description specification developed by Pixar and recently founded in alliance with Adobe, Apple, Autodesk, and NVIDIA to promote the standardization and evolution of this technology. And OpenVDB is a volumetric representational data format and a set of tools that we developed and we open sourced at DreamWorks that transformed movies. In fact, if you have seen a VFX movie or a TV show with explosions, fire, water, or fog since 2015, then you have definitely seen OpenVDB in action. It swept through our industry so rapidly that 4 of our developers won a SciTech Academy Award. This is the same academy that gives out the Oscars for it the very next year after we released it. And in fact, just last year, OpenVDB won their 2nd SciTech Award for its ongoing impact in the industry. This is tremendously fast for a SciTech Award that generally waits years to ensure that there is a positive impact in the industry, and we are very proud to have spearheaded that. So all renderers have a personality. This quote here about keeping all the lanes, this is our mantra and our personality and a key aspect of our vectorized architecture, and it is our guiding principle for development. Our goal was to achieve scalability up to real-time rendering, leveraging all the available hardware. The need to trace and shade billions of rays implied thin interfaces and no data structure redundancy. We also embraced data-oriented design. This is a methodology that you may have heard of that first grew in the games industry, but we applied it with great success on MoonRay. So compared to vectorization, which I'll discuss in a moment, multi-threading is quite straightforward. First, we divide the frame into 8x8 tiles. Idle threads pull the next tile from the queue and begin work. And we have some techniques to ensure that artists get a rough, pixelated image quickly and that computation proceeds without any locking. And so we avoid Amdahl's law of diminishing returns when coordination is required during multi-threading. And there are the results. This is exactly what we wanted to see, all threads fully loaded. Let's talk about vectorization. This is the process of setting up blocks of computation where the same instructions can be executed simultaneously on different data, or a single instruction, multiple data, SIMD as it's called in the industry. Modern chips provide a large number of vector lanes. MoonRay's ray data flows in and out of queues that prepares the data to be bundled into the SIMD vector pipeline. On AVX2 chipsets, for example, we can perform 8 operations for the price of 1. Let's look at some results. Here's Astrid from How to Train Your Dragon in a test T-pose. Now there's a lot of fur and hair in that scene, and the biggest block of time at the bottom in blue, the incoherent rays, is spent inside of Ombre, Intel's open source intersection library, as I said, that was developed in conjunction with and for MoonRay. Since Ombre is already well vectorized in both our scalar and our vector code paths, we don't expect an improvement in this area, nor do we see an improvement. However, we do observe significant gains in shading, texturing, and integration, and despite the overhead for vectorizing the scene, we see a good result with about 37% performance improvement overall. So in scenes with complex shading, with hair, et cetera, we see big improvements, well worth the gains for supporting this code path. Most commercial ray tracers are structured such that the DCC tool, like Maya, Houdini, Katana, Blender, etc., they run the renderer inside of their own process. This makes the process quite large, and if either the renderer or the application have a problem, both end up crashing. Eris is our thin layer API for rendering. The artist can start MoonRay as a separate process on the same computer, or they can run it on a separate computer. This enables the artist to use a lighter weight computer on the front end with a beefier back end for the rendering. Or for even better performance, you can distribute the rendering onto multiple remote blades to accelerate the interactive display for the artist. And thanks to not locking, the speed up obtained is linear with the amount of computation added. And this is robust to a failure of a node. If a remote computer fails for some reason, the render continues, but just that percentage slower. This architecture, while seemingly simple, has produced linear speedups on clusters of up to 96 hosts. That's the most we've tested because it's the most the R execs authorized us for testing purposes. And as you can see, at 40 hosts, we show 40 times speedup over a single, and a test from our Glendale location to 96 blades in the Azure West US region, we also saw a 96 times speedup over the single host. Each of these hosts had 120 gigabyte of memory, 64 hyper-threaded cores, and this, I believe, demonstrates the commitments we've had to never locking or waiting on the results of another computer or a computation. So Pixar released a scene description format called USD, or Universal Scene Description, which contains a definition for a Hydra render delegate that defines a common interface for renderers. And you can think of this like a PostScript interface. You've got many applications in the world that can write a PostScript file, and you've got many printers that can accept a PostScript file and print it. In a similar way, you can think of Hydra as a standard interface that eases the integration of renderers into artist tools, and we do support Hydra. Also in multi-machine and single machine mode. So a few artistic features. MoonRay supports the standard features you would expect in a production renderer, such as the ability to use light path expressions to select and isolate certain light paths in order to do post-rendering compositing operations. You can think of this as something like regular expressions for light. For example, we can use an LPE to perhaps distort the glossy reflection of an object to make it look otherworldly. We also have AOVs, or arbitrary output variables, which allow direct visualization of key material properties to discover anomalies or inconsistencies across characters and environments in order to ensure that we have well-behaved materials before the full production lighting phase begins. We can use these LPEs and AOVs as layers to input into pluggable display filters that take those shader outputs and do operations like cartoony post-processing and more. We can art direct many different looks and styles with MoonRay. In this example, I like the dust on that translucent shader on the right. So MoonRay at DreamWorks, it's battle tested, it's actively developed and in use at DreamWorks for our recent and upcoming feature films, such as The Wild Robot was our last release, and the upcoming Bad Guys 2, which is opening in just over a month. And as we continue to develop MoonRay's capabilities to support the ever-growing needs and ambitions of our feature film productions, we are excited, of course, to see how its open sourcing can make it even stronger. Just want to give you some idea of the kind of data. This is an average for one film. We consume a lot of CPU hours, a lot of cores, a lot of files, a lot of terabytes of data to produce one of our films. We generally have about 4 films in production at any given time. This would be an average across the length of an entire one film. More specifically to The Wild Robot, these are some fun stats that I pulled out from the show in terms of the number of objects that we are having to build and render to deliver the show. I'm not sure if people know, but the 100,000 plus control points on the Brightbill Teen, that just means the rig, basically, and how many joints we put into that rig for an artist to manipulate and do the animation. So it's a lot. It's a lot of data. Let's continue on. One second. So how did we get here? We made an initial proof of concept in 2012 as a project called Orchid. And our goals with this project were to demonstrate the relative ease with which we could assemble a functional MCRT core renderer, evaluate Intel's Embry as the underlying geometry ray tracing platform, identify areas in which work would be required in order to deliver a production solution, and do all of this quickly and without impacting our studio priorities and schedules. So here we're seeing an early demonstration of the Orchid proof of concept, focusing on fast time to first pixel for lighting changes. As the light source is moved around the scene and radiance values are modified. This demonstrates the ease an artist has to make fast iterations on the scene. Now in a second part here, we see the adjustment of material properties on a marble by decreasing its roughness and seeing how the light contribution changes. So what was next? Well, we needed to design it as an actual new renderer. We needed to implement what was missing in Embry. We needed to write the scene, procedural, shader, and sampling APIs, and we needed to plan for an open source product. To that end, we started an experiment in 2013 to produce an interactive renderer for rendering as a service with an effort called Nova. And for folks interested in the history of technology at DreamWorks, DreamWorks has long looked at how can they apply the technology that we build for feature films in other domains. And so this Nova effort was really about trying to bring rendering as a service in the cloud to other domains. It could be used for feature animation, but it could be used for product development and all kinds of things. So here's an early example demonstrating hair and makeup preview for a cosmetic company. And while you might think you've seen faster displays in video games, this simulation does subsurface scattering of light under the skin based on the thickness of the skin and pockets of fat. There is multiple scattering in the hair to emulate accurate hair lighting, and all humans have hair fuzz on their skin, and this model also includes that. MoonRay and Nova did many product designs, such as this simulated fabric and drapery designs in situ in a room environment. Oh, whoops. So the Nova initiative also drove the development of Eris for distributed multi-machine computation and integrated MoonRay well to add linear scale for rendering as the number of hosts is added to the computation. In this video, we are rendering Poppy from the movie Trolls on 14 hosts, each with 40 cores for a total of 560 cores. Each host had a Xeon 2.8 gigahertz CPU. As you noticed, that hair, the curves in the hair rendered very, very quickly when we zoomed in. That's the scale that you get with that kind of linear speed up. So our VFX supervisor on How to Train Your Dragon: The Hidden World, the Dragon 3, saw the results achieved with Nova, and in early 2018 made an impassioned plea for MCRT. So we were, up until that point, we had been working on our scanline renderer. And you know, rhyming rules must be followed. So the following, what I want to show, is a test scene that he set up to convince the executives. Now, he wanted to be sure that we knew this was only a test and is not final surfacing, lighting, rigging, or any of that. To be honest, I can't really tell. You likely won't be able to either, but I do need to point out, because he asked me to, this was just a test. Did you guys hear that? No? I was testing the sound, but it worked earlier, not now. Doesn't matter. This test convinced the execs that the look could be achieved with MoonRay. and could handle the complexity of dense foliage, shading complexity, the ease of lighting setup, and the speed of rendering, and his plea for MCRT was greenlit. I was fortunate to sit in the dailies room when the VFX supervisor, can you hear me? Yeah. When the VFX supervisor made his pitch to the execs, and the mood was electric. It was such a passionate pitch that this story, the world and its characters in it, deserved the richness that MoonRay would bring to the look of the film, and he was right. It is gorgeous and a beautiful film full of artistry. Of course, now that this particular technology was sold, the show still needed to get made, and we were on a deadline and with a fixed release date for that movie. We had a lot of work to add some required features into the renderer, as well as to get it running across the show's entire pipeline so that artists could use it. Our basic strategy on that was simple: defer anything and everything which had a workaround to achieve the show's look, and focus exclusively at first on those things which had absolutely no workaround. Nope. For instance, we needed to support crowds and volumes such as clouds, smoke, water, and fire. And in fact, at the time that we were greenlit to be used on the movie, we did not have a volumes integrator at all. And one of our engineers did brilliant work to develop one in time for the full production pipeline to ramp up. I will say that there were a lot of caffeinated drinks and very loud metal music involved in that delivery, so he loved it. There's nothing like a cool challenge to me, right? So many people think that How to Train Your Dragon: The Hidden World is about base-jumping Vikings, or the evolving relationship between a boy and his dragon, or the loss of loved ones, or the depiction of disability and characters that thrive nonetheless, and those are all true. This movie could have also been titled, in my opinion, How to Break Your Renderer, as it is also true that it is a movie all about some of the hardest rendering challenges to overcome. Many scenes with indirect light sources, depth of field, volumes of all sorts, clouds, fog, fire, water, and smoke. This is, incredibly, one very moody film. The acclaimed cinematographer Roger Deakins was a visual consultant, and it shows. So although The Hidden World was the first feature rendered with MoonRay, while its production pipeline was ramping up, we also rendered a short, Bilby, on MoonRay to test what was working and what we needed to improve. That short was first released at the Annecy Film Festival in 2018 and received a Jury's Choice Award at that year's SIGGRAPH conference. If you like, you can look this movie up on the internet and watch it in its full, sweet 8 minutes. It's a lovely little short, and I recommend it. So let's continue on. So, MoonRay sounds great. What an amazing technology. Why on earth did we open source it? Let's start with our timeline. We got the green light to open source in January of 2022, and though we'd been working on pitching the idea internally with our execs for about 1.5 years prior. Once we had that green light, we moved pretty quickly to initiate and start the project in March of that year, with an ambitious goal to release it by the end of the year. We reorganized our roadmap to carve out some activities on the project, which I'll discuss in the next slide, and the team got busier than they already were. We decided to announce our intent to open source at SIGGRAPH in August. That generated significant interest in the community, and we gave an impromptu presentation at the co-located open source days hosted by the Academy Software Foundation at that same time. And we invited people to sign up for news and beta testing, and a bit more than 4,000 people did so. The team continued working on getting everything ready, along with our normal development of our feature productions. However, we missed our internally set deadline for an end-of-the-year release. Basically, we knew by mid-November we weren't going to make it at the quality we felt we needed for the initial launch. And so we broke the news but committed ourselves to a Q1 launch in 2023, and that's just what we did. So we launched it live on March 15th, 2023. And since then, we made about 8 update releases, the latest just a couple of weeks ago. So we're averaging a new release every quarter at the moment. Our initial focus was on a few core items. Of these, the 2 largest were replacing the build system and standing up a robust documentation site. So we replaced our build system with CMake from Sconce. We extricated our code base from our internal library dependencies. We did some minor code cleanup and refactoring. And we stood up a brand new public documentation website, which updated all of our core set of user documentation, which was taken from a variety of wiki pages of questionable and ill repute, perhaps, and improved everything, adding videos and images to kind of show off the features. And we added in a search functionality. And this is our new go-to for all things MoonRay internally. Basically, our goal was to provide a system and documentation as thorough as possible, given our time deadline for first launch. That was by no means perfect or final, but we wanted to make sure that people would want to come back after a first visit. And we asked ourselves, if we were searching for an open source project, what would we minimally want to see? So I mentioned that we're updating our repos approximately every 2 to 3 months. So far, this has been a good cadence as we develop new features for our production and for us to stage our release and do all our regression tests, scans for FOSS hits, et cetera. We've been open source for 2 years now. What else have we been doing since then? Well, we released an entirely brand new test suite for regression testing to the open source community. This allows anybody to test performance or look regressions and improvements across new released or modified versions of MoonRay, add custom tests, and generally keep an eye on the stability of rendering. Our initial release was on CentOS 7. We now moved to supporting Rocky 9. We also released a branch of MoonRay that includes support for Presence Z, which is a technology that allows 6 degrees of freedom movement rendering for VR applications. And we've also, of course, accepted our first individual contributions. We're happy that folks have taken an interest in MoonRay, and we look forward to many more. We've also been working with partners to enhance MoonRay's capabilities and reach. Intel developed the Open Image Denoise library for CPU and GPU, and we'd like to thank them for contributing this back to MoonRay, and we're pleased to see this as part of our capabilities. We found that their 4004 Morehouse is a good asset to test and validate our Hydra implementation and compliance. And this video just kind of shows you what it looks like to run MoonRay standalone or with denoising or multi-machine and also with denoising. No. So in collaboration with the Metal Ecosystem Engineering team at Apple, we have MoonRay up and running seamlessly on Apple Silicon with full support for XPU mode using Metal. And thanks to Apple Silicon and its large unified memory pool that both the CPU and GPU can access, we have the ability to render large assets that are difficult to render when the BVH doesn't fit in the VRAM of a discrete GPU. In other words, it's amazing to see that we can run MoonRay comfortably on a laptop. So regarding why we chose to open source, we believe in the strength and resilience of the open source community, and we hope that MoonRay excites the community and allows the code base to grow stronger, and establish and develop partnerships with educational institutions, companies, and individuals. To be transparent, we do think MoonRay is a great tool in the arsenal for those who will adopt it, and there are selfish reasons for us to provide this technology to the open source community. We wanted to use MoonRay with partner studios, but there was no way for artists to learn MoonRay except inside our studio. We absolutely want this effort to extend MoonRay's reach. We want access to the smart, creative folks in the open source community. And it's already provided success. Intel has already provided integration into their new machine learning denoiser. We partnered with Apple, as I mentioned. And one last call out for contributors. Let's see. Sorry about that. We're a Linux shop, and we have our own processes for getting our software out to our own shows, so we don't feel like we have to own everything around MoonRay. There are lots of opportunities there for the entire world to use MoonRay that we can't specifically own, so we welcome experts in that field, and we want them to succeed and build reputation that way as well. I am running towards the end of my time, so I'm going to skip through a few slides very quickly here so I can sum up and take some questions. But some more highlights. I just wanted to demonstrate here a little bit about using MoonRay in areas that are not feature film animation. So we did partner with HP on building a material with their 3D printer where we could visualize a 3D printing image before they actually printed it so they can make corrections to it. This is the model that we developed. These are the results. I hope you know that the render is on the right and the real thing's on the left. We also, as I mentioned previously, we worked with Presence Z to render with their SDK in MoonRay, which allows 6 degrees of freedom of movement inside of a scene. This is a scene that we rendered from the studio Animal Logic. They open sourced a scene called A-Lab. This is that scene, and you are seeing us walk, or one of our engineers walk through this scene in itself. And in a second, you'll see him kind of back out of the bounding box. Yeah, so you can see, you can stack the boxes, and that's what gives you all your freedom of movement. We also did a real-time motion capture test with MoonRay and Eris, and we did it in early 2016 on our mocap stage. This configuration that we set up is a good example for the Eris framework. The test is showing real-time rendering with MoonRay. The front-end application is Autodesk Motion Builder on the left, which receives live mocap data and streams to the Eris backend. We dedicated 18 Eris hosts to the test, each with InfiniBand connections. The total core count was 40 cores per host times 18 hosts for 720 cores. The CPU was a 2.8 gigahertz Intel Xeon. The Eris backend consisted of 3 parts: 1 host for deformation, 2 hosts for wind and collision simulation, and 12 to 16 hosts for rendering with MoonRay. Our frame budget here was 41 milliseconds to render in order to achieve 24 frames a second. Within this 41 milliseconds, we needed to finish 2 phases for rendering. First, the render prep phase, which reads the scene data and the delta changes, and secondly, the MCRT phase, which calculates the ray intersections. Render prep took about 5 milliseconds, or 10% of our budget, and the MCRT phase took around 35 milliseconds, or 90% of our budget. As you can see, the latency was a couple of frames from the incoming live mocap data to the final render, but the overall throughput was 12 to 24 frames per second, and so we achieved our goal. I think it's quite impressive for a CPU-based renderer back almost 10 years ago in 2016. We also, Eris allows us to do multi-context workflow. Really quick, I'll skim through this, but an artist can load up 4 nodes in an Eris and get different lighting conditions on a single asset and start changing lights and see what does that asset look like under nighttime, daytime, dusk, dawn conditions, for instance. We can also do this across an entire workflow, or an entire sequence, not just an asset. Okay, a few key lessons we've learned from open sourcing. At first, we weren't sure how much attention the project would receive, and we were pleasantly surprised by the excitement that came from everybody in the community. People are excited to use it. We are happy to see people picking it up and adding to it and working on parts of MoonRay with us. Totally amazing. Timing for our initial release had some interesting perspective, and we had to juggle several key factors. Key among those was readiness to open source. As a proprietary internal and non-commercial tool, this meant a lot of build and configuration work and testing, along with exhaustive efforts to overhaul our documentation and some marketing website development. We needed to not impact our work on open sourcing to impact our work for future films. We needed executive sponsorship. And with all of that and more in mind, we did a good job in our initial release, or at least we feel so. Had we waited longer, we may have built our automation further along, but then we may have stretched the patience to deliver our product. And so overall, we're quite pleased. I am running fast here. Sorry. So yeah, if we would have done anything differently, in terms of specific focus, it would have been increasing our release frequency and increasing our transparency to the community, particularly our diligence on that release frequency, which is currently about once a quarter. We wanted to engage with our community more, give more visibility in our team, handling all of our feature development, bug fixes, building configuration, marketing, etc. And so, although we're small, we're ambitious, we're eager, and we're driven to see MoonRay succeed. A little bit more. To close on our motivation to open source, I mentioned some of the standard things that benefit most open source projects, and I want to touch on something more basic in having that desire to share, and that is a sense of accomplishment. We are tool builders, and one of the neatest things about this job is not just building the tool itself, but seeing it put to use, and particularly seeing it put to use in ways we never dreamed of. Artists do amazing work, and we often find ourselves surprised and delighted in the ambitious look of our films. And it is stunning to think that they made something with such beautiful imagery and emotions using tools that we built. We take pride in seeing what people do with our tools in this community. Why not share and expand that? After all, where does our sense of accomplishment come from? Watching people make something amazing from that which you've given, instructed, or instilled in them. And we are in a continuous cycle of being learners and being teachers. Open source is a virtuous circle. I watched the legendary skateboarder Rodney Mullen, inventor of the ollie and other street skating tricks, give a TED Talk comparing the skateboarding community to the open source community. He describes that the unique environment skaters play in drive the creation of new tricks, fostering prolific ingenuity purely for passion's sake. I'll quote him now, quote, "There is an intrinsic value to creating something for the sake of creating it. Better than that, there is this beauty of dropping it into a community of your own making and seeing it dispersed and seeing younger, more talented, just different talent take it to levels you could never imagine, because that lives on." End quote. And we wholeheartedly agree. Final thoughts, MoonRay's on a strong foundation. Development's always been on performance, but we continue to grow features for our ambitions, and we're excited to see it in the open source waters. So I'd like to thank MoonRay and the Eris teams for being great folks to work with, along with our community and the contributors, and thanks to the Linux Foundation for hosting the event, allowing me to introduce MoonRay to everybody in our journey to open source. And of course, a big thank you all for coming and joining my session. Apologies, I went a little bit over. Maybe I got time for a couple of questions if you guys like. And that's it. Any questions? I sped run through that. Your eyes are just, your brains are just awash in imagery. Please.
MoonRay is under the ASW store, independent.
At the moment, it is independent. We are focused on growing our community, but we have strong partnerships with the Academy Software Foundation. The question was, is MoonRay under the Academy Software Foundation? We do partner with them. We collaborate in terms of presentations, but no, we're not directly under them. Okay, well, thank you, everybody. Take care.